You ever stop and think about how your phone knows exactly where you are? I mean, right down to the street corner. Or how a pilot can fly a plane across a massive empty ocean with, no landmarks? Well, it all boils down to this amazing invisible grid, a system of imaginary lines that gives every single spot on Earth its own unique address. So today, we're going to unpack the story of latitude and longitude, this brilliant language we invented to make sense of our whole world.
Okay, so here's the big question. How do you pinpoint one exact spot on a giant spinning sphere? I mean, really think about that for a second. Our planet is just this massive, rotating ball, mostly covered in water, with zero natural permanent markers. Imagine you're adrift in the middle of the Pacific Ocean. How do you tell someone exactly where you are? This was one of the biggest scientific puzzles for centuries. It stumped the greatest minds, and honestly, it sent countless sailors to a tragic end.
You know, a globe isn't just a toy. It's a true miniature model of our planet. And it shows us a really key detail. Earth isn't a perfect circle. It's what's called an oblate spheroid, which is just a fancy way of saying it's a little bit squashed at the poles and bulges out at the equator, all because it's constantly spinning. Now, the globe in your classroom might have a little metal rod going through it to show the axis, but the real Earth, it spins on a completely imaginary line. There's no built-in up, down, left, or right. So you can see why creating a universal address system was such a huge challenge.
So to deal with all this chaos, we humans had to do what we do best, create a system. We had to impose some order. The solution was to invent a whole framework of reference points and imaginary lines that everyone could agree on. Without this shared system, global navigation, trade, even modern science as we know it, well, it would be pretty much impossible. This is the system that turns a huge unmarked ball into an ordered, navigable world.
All right, let's build this thing from the ground up. The very first piece of the puzzle, our first clue to this global address, involves drawing imaginary horizontal lines, or circles really, all the way around the globe. We call these the parallels of latitude, and they solve the first half of our problem, figuring out how far north or south any given location is.
Okay, every great system needs a starting point, right? A zero line that everyone agrees on. For measuring north and south, nature actually gave us the perfect one, the equator. It's that imaginary line that wraps around the widest part of the Earth, exactly halfway between the North and South poles. I mean, it's the only logical place to start. So we call it 0 degrees latitude, and it perfectly splits our world into the northern and southern hemispheres.
So from that starting point, all the other circles that run parallel to the equator, those are our lines of latitude. Now think about this for a sec. The distance from the equator to either one of the poles is exactly a quarter of a full circle around the Earth. And since a full circle is 360 degrees, a quarter of that is, 90 degrees. That's why the North Pole is at 90 degrees north and the South Pole is at 90 degrees south. It just makes perfect sense. And as you can see, these circles get smaller and smaller the farther you get from the equator, until they're just a single point right at the poles.
But here's the thing. Just having a number isn't enough. The direction is absolutely crucial. For example, take the city of Chandrapur in India. It's located on the 20-degree latitude line. But guess what? So is the city of Belo Horizonte in Brazil. The key difference? Chandrapur is 20 degrees north of the equator, while Belo Horizonte is 20 degrees south. That one little letter, N or S, makes all the difference in the world. It literally puts you on the correct half of the planet.
Okay, so we've cracked the north-south puzzle. We can now tell someone which horizontal slice of the Earth we're on. But that's only half the address, isn't it? How do we measure where we are from east to west? For that, we need a whole second set of imaginary lines, running vertically. These are the meridians of longitude.
So what about a place like Tonga and a place like Mauritius? Here's the problem. They're both at 20 degrees south latitude, but one's in the Pacific Ocean and the other's in the Indian Ocean. So how do we possibly tell them apart? Knowing you're at 20 degrees south is a good start, but it just puts you somewhere on this giant circle that goes all the way around the globe. We're definitely still missing a crucial piece of the puzzle.
And that missing piece is the meridians of longitude. Now, these are different from latitude lines. Instead of being parallel circles, they are vertical semicircles that all meet up at the poles. A really important difference to remember is that while lines of latitude are always parallel, the distance between lines of longitude is actually widest at the equator, and then it shrinks all the way down to 0 as they all come together at the north and south poles.
Now, here's where it got tricky. Unlike the equator, there's no natural starting point for longitude. I mean, every meridian is exactly the same as the next. For centuries, this was just chaos. Different countries used their own capital cities as a starting point. The whole problem was finally sorted out in 1884. By international agreement, Everyone decided that the meridian running through the Royal Observatory in Greenwich, England would be the 0-degree line, the Prime Meridian. It was a practical choice, really. Britain was the world's biggest maritime power back then, and their maps were used everywhere. And just like that, this line officially divides the Earth into the eastern and western hemispheres.
So, starting from the Prime Meridian at 0 degrees, we measure 180 degrees to the east and 180 degrees to the west. And guess where those two lines meet? Right on the opposite side of the globe. That 180-degree meridian forms the basis for what we now call the International Dateline. And with that, we finally have it, the second coordinate we desperately needed, a precise east or west measurement. So, there we have it, our two key ingredients. We've got the parallels of latitude, telling us our north-south position, and the meridians of longitude for our east-west position. Now, on their own, they're pretty useful, but when you put them together, that's when you unlock a system of incredible power and elegance.
So here you can see the two systems on their own. On the left, you've got those horizontal parallel rings of latitude, and on the right, the vertical pole-to-pole semicircles of longitude. Each one solves exactly half the problem. But the real magic, the big aha moment in mapmaking, happens when you lay one right on top of the other.
And you get the grid. This incredible network of intersecting lines covers the entire globe like a giant spherical piece of graph paper. And the beautiful thing is, every single point where these lines cross is unique. There's only one of them. This is the breakthrough. It's what allows us to give a one-of-a-kind coordinate pair, a specific latitude and a specific longitude, to any spot on the entire surface of the Earth.
Let's see just how powerful this is. Take the town of Dhubri in Assam, India. Its location is 26 degrees north latitude and 90 degrees east longitude. Now think about that. There is only one single point on the entire planet where the 26th north parallel crosses the 90th east meridian. And that precise intersection is Dhubri. The problem is solved. We now have a totally unique, absolute address for any place on Earth. Incredible.
But you know what? This grid is so much more than just a way to find a location. These imaginary lines have profound, real-world consequences. So first, let's talk about how your latitude, your north-south position, directly and dramatically shapes the very climate you live in.
Okay, the easiest way to get this is to think of the sun's energy like a flashlight. Near the equator, the Earth's curved surface is facing the sun head-on. It's like shining that flashlight straight down onto a table. The light is super bright, the energy is concentrated in a small circle, and it delivers a ton of heat. But as you move up towards the poles, the Earth's surface curves away. Now the sun's rays hit at a sharp angle. It's like shining that same flashlight on a slanted surface. The same amount of energy gets spread out over a much bigger area, making it way less intense and a lot less hot.
And this simple idea, the angle of the sunlight, is what creates our planet's major climate zones. So first up is the Torrid zone. It's nestled between two important lines of latitude, the Tropic of Cancer in the north and the Tropic of Capricorn in the south. This is the tropics, basically, where the sun is directly overhead at some point in the year, just blasting it with direct heat. Then you have the temperate zones. This is where the sun's rays are always coming in at an angle, which is why you get distinct seasons, warm summers, cool winters. And finally, way out at the ends are the frigid zones, past the Arctic and Antarctic circles. They get the most slanted rays of all. The sun is always low in the sky there, which means extreme cold and crazy stuff like the midnight sun. In a lot of ways, your latitude is basically your climate destiny.
So, if latitude is all about climate, then what about longitude? What's its big job? Well, the lines of longitude, the ones running from pole to pole, are fundamentally tied to something else entirely, the rotation of the Earth. And because of that, longitude dictates our time.
And this right here, this number, is the master key to global time. Think about it. The Earth spins one full circle, 360 degrees, in about 24 hours. So if you just do the quick math, 360 degrees divided by 24 hours, you get exactly 15. Every single hour, our planet spins 15 degrees of longitude. This direct, unchangeable relationship is the bedrock of our entire system of time zones.
So here's how that simple math translates to the time on your watch. Because the Earth spins eastward, places to the east of the Prime Meridian in Greenwich see the sun first, right? So their time is ahead. And places to the west are, you guessed it, behind. The calculation is actually beautiful in its simplicity. For every 15 degrees of longitude you go east, you add an hour. For every 15 degrees you go west, you subtract an hour. It's like a giant global clock written right into the geometry of our planet. Let's make this super clear with a real-world example. India sets its standard time based on the meridian at 82.5 degrees east longitude. So when you do the math, 82.5 divided by 15 degrees per hour, you get exactly 5.5. That means India is precisely 5.5 hours ahead of London. And this has real consequences. A cricket match that starts at a perfectly reasonable 2 p.m. in London won't even kick off until 7:30 p.m. in India, often finishing super late at night. That's longitude in action, right there.
So we've been talking about this system of imaginary lines, right? A concept that was refined over centuries for sailors on wooden ships using paper maps. And yet, this old system, this grid, is the absolute foundation of our most modern technology. I mean, the GPS in your pocket doesn't invent some new system. It uses a whole constellation of satellites, each one a hyper-accurate clock, to figure out its own precise latitude and longitude. The fundamental language is exactly the same. So the next time you ask your phone for directions, just take a second to remember the elegant, centuries-old grid that makes it all possible, connecting satellites way up in orbit to the palm of your hand.